In March 2011, a wave up to 40 meters tall crossed the Japanese coastline. It left behind thousands of casualties, and entire municipalities reduced to standing water and debris. At ground level, the devastation revealed an engineering failure. The existing seawalls, designed to protect these coastal communities, were completely obliterated. 90% of them failed in a single hour. These structures failed because the arriving water crested the top of the barrier and cascaded down the landward side. The impact from the front was secondary to the destruction caused from above. That overtopping water violently washed away the soil holding the wall up from behind. With its structural support removed, the massive concrete barriers collapsed backward under their own weight. The second failure mode happened during the backwash. The extreme vacuum of the retreating ocean pulled the foundation sand directly out from underneath the seaward edge of the wall, causing it to collapse forward. A solid concrete wall is useless if the ground beneath and behind it washes away. True coastal defense requires a deeply integrated geotechnical system, anchoring the structure into the earth itself. Solving that physical reality led to a $12 billion coastal defense project spanning 400 continuous kilometers. Every meter required zero-tolerance construction specifications. Fortifying the front of a concrete block is pointless. To survive the hydrodynamic forces of an entire ocean, engineers had to completely redesign the subsurface foundation and the rear embankment first. This diagram maps out the immediate problem. Across 400 kilometers of coastline, the ocean floor changes drastically. Engineers had to design completely different foundation structures, depending on whether they were building on hard rock, dense sand, or soft mud. In the coastal clay zones, the ground is so dangerously soft it cannot even support the weight of a standard bulldozer. Construction crews had to lay down heavy steel road plates just to spread the load and keep their machinery from sinking into the mud. To build the foundation, divers guided 5-ton boulders into position 25 meters underwater in the active surf zone. Because the underwater visibility was virtually zero, they had to rely entirely on sonar data to lock the massive stones into place. After weeks of blind underwater placement, the massive rubble mound breaks the surface of the sea. Now we reach the most critical subsurface component. This visual shows a geotextile membrane. It is laid directly over the rubble mound before the rest of the wall is built on top. The membrane functions as a highly specific filter. It allows water to flow freely through the structure, but it traps the fine soil particles above, stopping them from migrating down into the porous rubble mound. If this fabric layer is missing or torn, the soil slowly bleeds away into the ocean. The mound settles unevenly, the foundation tilts, and the entire wall fails. The rubble mound itself is graded to a precise 1 to 1.5 slope angle. Any steeper, and the heavy boulders slide out of position. Any flatter, and arriving waves won't break optimally against the structure. The long-term survival of this multi-billion-dollar concrete superstructure relies entirely on an invisible fabric layer buried beneath the ocean surface. To defend against backwash scour pulling out the foundation sand, engineers drove steel sheet piles 10 meters deep into the ocean floor, anchoring them directly at the toe of the wall. Look closely at the edges of these sheets. They feature Z-profile interlocks, allowing each individual steel panel to slide into and lock tightly against the next. This specific interlock transfers shear forces across the entire alignment. Instead of thousands of individual steel plates, the wall acts as a single, unified anchor, resisting the massive vacuum of the retreating ocean. With the foundation secured, contractors began building the core of the wall. The embankment fill had to be placed and compacted in exact 300mm lifts, no more, no less. This comparison illustrates the strict mathematical threshold for that compaction, 98% proctor density. If the compaction falls below 98%, as seen on the right, the fill sinks and shifts under pressure, shutting down the entire job site. Right down the middle of that dense fill, engineers added a highly compacted clay core. This acts as internal waterproofing, stopping ocean water from permeating through the embankment and causing internal slumping.
The impenetrable concrete exterior is supported by an earthen core built with ruthless, microscopic soil compaction discipline on the inside. Covering that earthen core is the seaward face, assembled from thousands of 7-ton CNC-machined concrete panels. every single joint between them requires zero-tolerance alignment. This is what that flawless alignment looks like when successfully assembled across a curved stretch of coastline. To keep an arriving tsunami from ripping those massive panels off the wall, U-shaped steel hairpin rebars lock the top of every single facing panel directly into the solid crown wall, running along the peak. Look at the geometry of that top crown wall segment. It is angled exactly 10 degrees outward from the vertical plane. That specific 10-degree angle catches overtopping water and physically throws it back toward the ocean, rather than letting it crash onto the vulnerable foundation. Out in front of the wall, engineers deployed massive passive energy absorbers, a dense armor layer of 32-ton interlocking concrete tetrapods. The weight of these blocks isn't a guess. It is calculated using the van der Meer equation, taking local wave height and energy variables to output the precise minimum weight required for each individual armor block. As they are dropped into position, the chaotic gaps forming between the tetrapods act as a mechanism. They force arriving water to flow through a complex labyrinth, dissipating the kinetic energy of a massive wave before it reaches the main wall. And if water still manages to overtop the crown, a dedicated concrete drainage network built into the landward side safely channels the runoff away, protecting the rear soil from eroding. Modern seawalls survive by redirecting, fracturing, and absorbing millions of tons of kinetic energy across multiple specialized structural zones. But a 400-kilometer wall contains a severe vulnerability. To keep the coastal economy alive, engineers had to leave 443 gaps completely open for rivers, working ports, and roads. Securing those openings requires massive integrated hardware, like this concrete and steel tsunami floodgate spanning a river mouth. When an earthquake strikes, embedded seismic sensors trigger instantly. Bypassing human input entirely, the system initiates a strict 70-second closure window, dropping 50 tons of steel to seal the river before the wave arrives. The machining tolerances on these gates are brutal. During that high-speed drop, the steel maintains just 15 millimeters of clearance along the tracks. This cross-section shows the hydrophysics at play if that seal isn't perfect. Under extreme tsunami pressure, a gap of just 2 millimeters instantly forces 40 liters of water through per minute, rapidly grinding the opening wider and failing the entire gate. To guarantee deployment, the gates are stored in the open position at the top of the towers. Even if the local power grid is completely destroyed by an earthquake, gravity brings the seals down. The most impenetrable static concrete wall on Earth is entirely useless without flawless, automated kinetic seals immediately plugging the holes in the armor. The completed megastructure operates as a living system. Thousands of embedded sensors constantly feed live telemetry data back to the central command center. Engineers obsessively track differential settlement, measuring exactly how the thousands of individual concrete and soil segments shift across 400 kilometers of highly varied coastal terrain. This map visualizes the telemetry data from the first 2 years of operation. Across the entire 400-kilometer network, the sensors recorded an absolute maximum of 14 millimeters of differential settlement. Then came the ultimate stress test. A massive 7.4 magnitude earthquake struck the coast, violently shaking the freshly settled foundation. The automated network fired instantly. Within seconds, all 443 independent floodgates deployed and sealed simultaneously, locking down every gap along the shoreline. In the aftermath, structural inspections returned an exceptional result: 0 cracks in the concrete panels, 0 shifted armor tetrapods, and absolutely 0 structural foundation failure. Today, the extreme geotechnical violence engineered into the design stands in sharp contrast to its surroundings. For the locals living behind the barrier, the top of the wall simply serves as a quiet daily promenade. Japan conquered the hydrodynamic forces of an entire ocean by obsessively controlling microscopic thresholds. In modern engineering, macro-scale survival is dictated entirely by millimeter-scale precision.